Okay, good evening everyone. So today is the last class, last tutorial for this superconductivity course. If you have any question, please ask. Am I audible?
Yes, you are audible.
Okay. So if there are no queries, then today we'll mostly do Josephson junction and squid, and the assignment 4 is also almost every question is related to that. Okay. So Josephson junction is basically we have two superconductors and then it is connected via some weak links. Okay. So this is, let's say, superconducting region 1, and then this is 2, and this part is let's say normal metal, or often it becomes actually it is used as insulators. Okay. And this width of this part insulator or the non-superconducting region is actually very less compared to the superconducting region. So if they are very far apart, let's say something like this, then of course there is no interaction because it's an insulator. So it cannot carry any charge. So this SC1 and SC2 are decoupled. Okay. So that's not the Josephson junction. So we have Josephson junction when they are connected, the two superconductor are connected by a very thin layer of insulator or normal metal, so that there is a connection between these two. Okay, and if you apply, let's say, voltage here, then the current can go from one region to another region. If it becomes too wide, then it's just disconnected. So we'll see how this current, in this kind of junction looks like, and what are the features and what are the advantages of it. Okay, so we initially see some basic equation, Josephson equation 1 and 2, and then we'll move to the uh, assignment parts. So in the last class, we had this second Ginsburg-Landau equation, right? So what this says is that what will be the current expression in a superconductor if we have so let's say assume that we have psi as the wave function of the superconducting electrons or the Cooper pairs, and then we apply external magnetic field which is connected or I mean uh, reflected in A, because curl of A is B, right? So we'll use this equation to derive a generic uh, so expression involving current density and then a magnetic flux. Okay, so we had equations something like uh, so so this is the second Ginsburg-Landau equation. So it says that current density is given as minus I E h bar by 2m. So here m is the electronic mass. Okay, so in this equation where we had m star is nothing but 2me, because Cooper pair consists of two electrons, and here q is also minus 2e. Okay, okay, so we use this. M star equal to 2m of electron, let's say, but equivalently I'll write just m, and then q is also minus 2e. So if we use this, we have equation something like this: psi star grad psi minus psi grad psi star uh, minus 2e square by m a mod psi square. Okay, Okay, now if we assume that psi can be written as psi 0 e to the power I phi, where psi 0 is constant, so it is some constant, and it's kind of psi 0 is equivalent to root over n. N is the superconducting number density in the system. So and then phi depends on R. Okay, so whatever the gradient term here, a gradient term only operates on phi. Okay, uh, so so we have a phase to be phase to vary in space, but I mean the amplitude of the wave function is constant. So grad psi 0 is 0, whereas sorry, grad of phi is not equal to 0. Okay, so in a superconductor, the phase is varying in space. And this, yeah, so if we use this particular information, then from this, let's say this is equation 1. Equation 1 we can write as J equal to E h bar by m psi 0 square gradient of phi. So what we have done is that we use this part in equation 1 and evaluated this. Okay, psi star grad psi and minus psi grad psi star. And then the other term p square by m a psi 0 square. Okay. Now we divide this whole equation by so divide and integrate over space, some closed loop. Okay. So the equation will be, so this equation, so I'm dividing by EH by m psi square. So, so it will be m by EH, and then okay, so let me first do it. Now we integrate over a let's say closed loop C. Okay, so we have a sum loop which we call C, and we are integrating. So what we have is J dot dl. So dl is the elemental area here, somewhere here in the closed loop, and then mod psi square equal to, so this part cancels out, this also cancels out because psi 0 square mod square is equivalent to psi square, right? E to the power I phi and e to the power minus I phi just cancels out, So we have a closed loop integral over grad phi dot dl, and then what we have done is that again closed loop integral of a dot dl, and there will be some factor here. So this m will cancel, e will cancel, and then h 2 by h will be there, but then we send 2 by h in this side, okay, so that h bar of this side vanishes, okay. So if we do this, then the final equation becomes m by 2 e square j dot dl, so small j, by mod psi square plus this is equal to actually, or no, uh, so I'm taking this at this side, so plus phi of b equal to uh, grad phi dot dl, okay. Now this phi of b is closed loop integral over a I mean in path C, and this is actually nothing but the magnetic flux. So imagine, so what we have done is that we chose a path closed loop path in within the superconductor, and also there is a magnetic field already applied, as you have done in the second Ginsburg-Landau equation. So this A dot dl can be written as using Stokes theorem. So S is the surface area enclosed by closed loop C. Then it can be written as B dot ds, right? So this means that phi B is nothing but the magnetic flux uh, through this closed loop or the surfaces. Okay. So this is the equation actually. Okay. Now the one important point is that this grad phi dot dl, it cannot take arbitrary value. It has to be some it will be some unit of uh, fundamental uh, flux quantization. And this is because so the phi has to be, so let's say we have a closed loop something like this, and then superconducting wave function psi varies over this space, right? Because we have a grad phi, and this the phase cannot vary arbitrarily because let's say I start from here, I have a I mean wave function somewhere here, and then it varies over space, okay. Now it has to be single valued, the wave function is always single valued, okay. Otherwise it's not well defined wave function. So this single valuedness can come from, actually we can show that whenever we have, I mean, applied magnetic field, then psi goes as psi 0 e to the power closed loop a dot dl. In general, it's not closed loop, but if we take closed loop, then it will be, of course, closed loop. But in general, along some path psi, sorry, c. So let's say this is the path, not closed. So then psi goes like this. Okay. So if we start from here and then end here. Now, the moment you close this loop somewhere here, you are coming back at the same point. Then it has to be, the phase acquired by the wave function has to be such that psi come back to the psi, and that condition and because of this psi is should be equal to psi once we traverse back to the same point. From this particular condition, from this condition, it turns out that the grad phi dot dl has to be uh, in integer function of n, and phi is as always h by 2e for superconducting case, or in general what we call phi 0 is h by e. But for superconductor, again for Cooper pairs, the charge is 2e, and n is some integer. N can be 0, 1, 2, and so on. Okay. Okay, so this is an important equation which we'll use in the Squid and Josephson equation as well. So m by 2 e square. Okay. Now let's come back to the Josephson junction case. Okay. So let's call it equation 3. So now imagine we have a superconducting region and then a very small insulating region. So we have, let's say, left superconductor and then right superconductor, and then this is the insulating region. Okay. And the voltage is applied. So some voltage is applied. So what will be the wave function over for these regions? Let's say, so this is the superconductor, left and right. So so for the left region, so somewhere here, let's say, so I should not draw. Okay, fine. So along this, let's say this is extended like this, and this is extended. So I start from somewhere here, okay, within the superconducting region. So then deep within the superconducting region, my wave function is having a some maximum value. It's independent of position, let's say, and then it should decay as we go away from the superconducting region, right? So left superconducting wave function something looks like something like this, and then similarly for the right it will be similar, something like this will look like. Okay. And this also explains that if you have very I mean very, so this region, insulating region, if it is very big, then this wave function quickly die out, right? So, imagine a situation where we have something like this, right? And wave function for the left superconducting region dies out like this, and then right dies out like this, right? And it is, let's say, this is the zero value. So if you have this wide region of insulating region, then there is no kind of superposition, and then there is no connection between left and right part. So this also explains that this part needs to be smaller, so that there is a finite overlap between the left and right, so that there is a current can pass and interesting things can happen, as you'll see later. Okay. Okay, so the so for the left, let's say the wave function is psi L with again psi 0 and then e to the power I phi L. So phi L is the phase for the left superconducting region, and then similarly psi R is psi 0 I phi R. Okay, so we are taking psi 0 in both the cases because we are assuming that both the in both the region left and right made of same superconducting material. Okay, and they are put in same condition, and that's what it happens. I mean experimental or practically also, so that they have the same. I mean the amplitude part. Okay, so now what we are interested in is that what will be the current and what will be the phase difference. So we are interested in two things. So one is current. So we have already applied voltage, and then there is two superconducting region separated by small insulating region. So what will be the current across this junction? And then second is the what is the phase difference between these two superconductor because of application of let's say voltage. Okay. So these are the two things we want to calculate, and these two equations that we will get, which will tell me what will be the current and what will be the phase difference, are called two Josephson equation. So to derive that, we will use a Schrodinger equation. So time dependent Schrodinger equation is I h bar del psi del t equal to energy times the psi, right? Now for the left superconducting region, we have I h bar del psi L del t, and then equal to energy for the left. So this is the ground state energy for electrons in the left superconducting region. Psi L plus, there will be something I'll write later. For right, again the same thing, psi R, right? Now the important point comes that uh, these two regions are coupled, right? They are essentially weakly coupled, but they are coupled. So assume that coupling constant is K or kappa. So then if we have coupling, then so this is the coupling that appears in the left. So note that this is the right superconducting wave function. I mean wave function for the right region actually. Okay, because these wave functions here overlaps with each other. So the right part comes and overlaps with in some region with the left part, and then the vice versa, so that we have a coupling in the equation itself also. Okay, and we assume that the coupling for both the cases is same. It's just the wave function that gets. So so these two are coupled equation we need to solve. Okay, so any questions so far? Okay, now okay, so let me call it equation 4. So if the, I mean, if the voltage is zero, so when there is no voltage applied, then of course left and right region's energy is some constant energy which we can again scale it to zero, let's say. Then nothing interesting happens. If you don't apply voltage, there is two superconducting region just separated by some insulating region, then it's nothing interesting. So because this will remain as a superconducting region, this will also remain as a separate superconducting region, so no interesting things. And you can also see from here also. So if EL and ER is sort of uh, constant, then you just scale it. This constant energy can always be scaled it to zero energy, and then there is no dynamics. That is the point. Okay, so that del psi L del t equal to 0, and del psi R del t equal to 0. So no dynamics. So both the superconducting region are in equilibrium position, equilibrium state. Okay. Now when V is not equal to 0, some voltage is applied. Then what really happens is that uh, so the voltage, so for our convenience actually, so you imagine that the voltage is applied in such a way that difference between these two, left and right, is 2eV, right? And this we can always write, right? Because 2e is again associated with the Cooper pair energy, I'm sorry, charge, and then V is the applied voltage. Okay, so what we are essentially saying is that we rescale the energy so that we imagine that this is the zero energy scale, and then the for the left region, uh, yeah, actually this 2 is not associated with Cooper pair. So let me explain. So EL is at, let's say, EV, and ER is at minus EV. Okay, so this is just the rescaling of energy, and this doesn't change any physics. So that their energy separation is 2eV. So that 2eV is coming here. It's not associated with Cooper pair. And these are all we are doing because of, I mean, so that the calculation becomes easier. Okay, So for the left part, we have EL to be EV. So I H bar del psi L del T equal to EV psi L plus coupling. And then for the right part also equal to minus EV psi R plus coupling part. Okay. Okay. So now we use psi as root over of, let's say, rho, or I can call it also n e to the power I phi, right? So psi was usually psi 0 e to the power I phi, no, but psi 0 mod psi 0 square gives me the density of superconducting pairs. So what we write is as psi 0 as written as root over of n. Okay. So we use this equation in this equation, let's say, then we have uh, I h bar by 2 root over n L. So this should be n L to the power minus of e to the power I phi L del NL del T. Okay, so this is because root, I mean, derivative of root x is 1 by root x. So this part is taken care of by NL to the power minus of, and then the derivative minus h bar NL to the power half e to the power I phi L. So the iota comes, so the del T of e to the power I phi L will give me an extra iota, and this iota and this iota will give me extra minus sign. Okay, I'm not showing the all the steps. And then del phi L del T equal to uh, very NL okay. Similarly for the right side, or actually without writing right side, we can simplify this a bit. So finally we write it as just the reorganization of the terms, NL 1 by NL, and then del NL del T minus del phi L del T equal to EV by h bar plus coupling by h bar. So NR by NL root over root, and then e to the power I phi R minus phi L. Okay. Now this phi R minus phi L is the phase difference between the two. I mean between the two superconducting wave function. Okay. Okay. Now this equation, let's say 5, and then it have two parts. One is real part. So this is, let's say, real part, and then there is also imaginary part, right? So the real part will also come from here and here. So equating real and part of equation 5, and both RHS, and so left hand side and right hand side, what we get is that NL minus 1 by 2 del NL by del T equal to K by H, and then NR by NL square root sine delta. Okay, So why sine? Because this part's imaginary part is sine, and then this iota makes it imaginary. Okay, and then the other part is, so this is for from the imaginary part. Okay, and then from the real part you will get del phi L del T equal to minus EV by h bar minus k by h bar. So nr by nl of cos delta. Okay, so this is from the real part. Okay, then similarly we can do the similar calculation for the right region, so superconducting region from the right side, and then we will get the very similar equation, del phi r del t equal to EV by h bar minus k by h bar n L by nr half cos delta, and also the density equation, so del nr del t nr minus 1 by 2 equal to k by h bar nl by nr square root sine delta. Okay, so these are the four equation, I mean the solution that we get. Okay, now okay, so now look at this equation. Let's say so this is, let's say, a, or what should I call it, 5. Okay, so this is 6 7. Now from equation 7 and equation 8, right? Equation 7 and 8, we have del phi r del t minus del phi l del t equal to 2ev by h bar. Okay, and this we can write as del delta of t equal to 2ev by h bar. So this is the second Josephson equation. Okay, so what it tells is that the phase difference between the two region, the left region and right region, is I mean the time derivative. So the rate at which the phase difference changes is directly proportional to the voltage that has been applied in the Josephson junction. Okay, so this is the second, and then the current. Uh, so the current density. So supercurrent density, supercurrent because the current is essentially carried by the Cooper pairs in the superconducting state. Supercurrent density flowing across the junction. So J is nothing but minus 2e, minus 2e because again the Cooper pair charge is minus 2e, and then del rho L del T, let's say, right? So the change in the density, Cooper pair density from the left to right. So if we go to our figure, so this was the left region, and then this was the right region. So this is the positive voltage and negative voltage. So the current flows here. So that's why we have taken that how much, I mean, so the decrease in the or the time with, I mean the density change with respect to time. So if we calculate this, then so we already had this equation del rho del t. So this is the uh, Actually, this should not be written as rho. I have taken n as the, so NL is the density, so Cooper pair density. Okay, so if you use equation 6, this equation, okay, then what we can write is that, so this will be equal to minus 2e uh, and then k by h bar, 2k by h bar, then del nr of sine delta. Okay, so use equation 6, and this we can write as some j0 sine delta. Okay, where j0 will be uh, with j0 being minus 4k n. Here we write n is what, nl nr square root. Okay, so nl and nr are always I mean almost same, because the I mean Josephson junction are always made of similar material, or in fact the same material actually. So same material at the same condition will have similar supercurrent or Cooper pair density, right? So that's why the left region and right region have similar density of Cooper pairs. And then so that means the n is the total density of Cooper pairs. Okay, this is the total density, or rather effective. I should not call it total, but effective. Okay, so 4k n by h bar. So this is the first Josephson equation. Okay, so so both the current. So we wanted to calculate current across the junction, both the current and then the phase difference between the two superconducting region. Both of them are actually associated with I mean the so what I'm trying to say. Okay, so actually, yeah. So the phase difference is associated with the applied voltage, as you can see from here. But then the current, mm, wait, charge. Okay. Then but the current is again dependent on the phase difference that you create. Okay. So if the phase difference is getting changed over time, then the current across the junction is also going to change. Okay. So this is something non-trivial, because in a normal material or normal conductor, if you apply current, then we have a steady current, right? After very quickly, after within fraction of second, we get a steady current, as long as the your voltage is fixed. But that's not what happens here. In your I mean Josephson junction, we have a current to be a function of time. Okay. So So this phase difference can be rewritten as, so delta del t is, we had 2ev by h bar. So this we can write as 2e by h, 2 pi v. So this is 2 pi by phi 0 v. Okay, and then phi 0 is of course h by 2e. Okay, so this is the actually key principle behind the working of uh, squid as well. So any questions? If you don't, yeah. Okay, so if there is no question, so let me go to the assignments. So there are other things I thought I will do, especially how Josephson junction helps in determining the small magnetic field. Okay, it turns out that as the magnetic field changes within a region, if we move the the Josephson junction, then the current through this Josephson junction will change, and that helps in detection of magnetic field. It as actually the Josephson junction using this principle of this that the current will be a function of I mean the phase difference, and then also the phase difference will also dependent on the voltage and so on. These things actually give rise to the working principle of squid. Now in Josephson junction, using this you can actually measure magnetic field of the order of zero point 0.1. I think it will be Gauss actually. Okay, this itself is a pretty I mean uh, small magnetic field. So 1 Tesla is roughly, it's not roughly, it is equal to 10 to the power 4 Gauss, right? And this 1 Tesla field is not very high in a sense that it is routinely available in experimental setups. Okay, although yeah, now we can go up to zero point 0.1 Tesla using Josephson junction. Okay, but using squid we can go actually much below than that. It turns out that um, so the calculation itself will reveal. I'll, I'll I'll try to do if we get time after the assignments. So we can detect actually 10 to the power minus 8 Gauss of magnetic fields. This is a very small magnetic field. Okay. Okay. Let's move to the assignments and then we'll come back if there is time. So any questions? Okay. So the first question is describe the working principle of a squid and what are its application. So VI characteristics of, so we'll do later actually because this question itself will take almost the whole time. Second question is again what are the main assumptions? Let me put here. So yeah, the second question is what are the main assumption of Fermi liquid theory and describe the conjecture of adiabatic continuity. What are the signature of breakdown of Fermi liquid theory? So this has been discussed in one of the lectures actually. So the assumption of Fermi liquid theory is that so there are quite a few assumptions, but the key assumptions are so the key assumptions are Pauli exclusion principle remains valid even in presence of interaction. So Pauli exclusion principle, and then second assumption is so whatever the good quantum numbers were, so good quantum numbers for both the interacting, sorry, initially we had non-interacting and then Fermi liquid goes to interacting, weakly interacting case. So interacting and then non-interacting, weak non-interacting and then weakly interacting. In both the cases, the good quantum number, whatever the good quantum number was in the non-interacting case, it remains same for the weakly interacting case as well. For example, so in solid state system, one one canonical case for good quantum number is crystal momentum. Okay, so this is a good quantum number. And then for even for weakly interacting, it remains valid. So that's what it says. And then the excitations are essentially quasi-particles, and the assumption is that the excitations are not purely, I mean, the whatever it was there for the non-interacting case, it gets renormalized. So the quasi-particles are the excitation in uh, interacting case or weakly interacting case where their effective mass also changes. Okay, energy also gets renormalized because of interaction. So these are the three main assumptions. Okay, so adiabatic continuity and so on is explained in the lecture. So you can see the lecture actually, that's much better. Okay, so the question 3 is write down the Josephson equation for current and voltage across a tunnel junction between two superconductors, and then explain AC and DC Josephson effect. Compute wave function and hence current inside tunnel barrier of width A. Okay. So this we can do actually. Okay. So we have seen that for Josephson junction, current is essentially current. What we have seen is that J equal to J0 sine of delta, right? So this was the equation. So this one, right? So the first Josephson equation. Now this we can rewrite, just this was the current density, and then we can write in terms of current. So IC I am writing. So this J0 is also called the critical current. Okay, and then sine delta. And the delta was difference between, let's say, I mean left and right superconducting phase. And we had a function that del of delta del t equal to 2 ev by h bar. So now here we have a given geometry that so have a potential minus a by 2, and yeah. So this is nothing but the same scenario as we had in the previous Josephson case. So superconducting region left, let's say, and then superconducting region right. But then there is a insulating, and this insulating case here works as a energy barrier. Okay, and we had a initial energy, let's say E0, or we took it as EL and ER in our case. Okay, so now the point is uh, so from this equation we can write as I of time equal to critical current sine of 2 EV by h bar, right? Uh, this this is how we get it. So this just we just integrate delta with respect to time. So let's say, so 0 to t, 0 to, let's say, delta, del delta equal to 2 EV by h bar 0 to t dt, right? And once you integrate it, you will get the delta equal to simply 2 EV by h bar t. So if we use this, we use this here. Okay, so delta equal to this. So this is the AC Josephson effect, where current varies in time. Now what happens if we have del phi del t equal to 0? Okay, so what does that mean is that V is itself 0. We have not applied any voltage across the I mean Josephson junction. So then we'll have, I mean, so del phi del equal to 0 means we have some constant, let's say. So so delta equal to some constant, let's say delta 0. Okay, and then I will have I again from here. I will be some again constant, then sine of delta 0. So this is the DC Josephson effect. This is the only two difference. The next question was uh, compute the wave function and hence the current inside a tunnel barrier of width A. Okay. So next we need to calculate the current. So we have a tunnel barrier of this is the width, let's say A. So imagine we have a nothing is said, but then imagine we have this height to be let's say V0. Okay, and then the energy from this side is E0 for simplicity. And we assume, of course, one dimensional case. Then the Schrodinger, again the Schrodinger equation will be uh, here we'll take the time independent Schrodinger equation h bar square by 2m and this m star. So d2 psi dx2 equal to E0 minus V0 of psi, right? Okay. Now this kind of equation have a very standard solution in quantum mechanics, where psi x will be given by C1 cos I cos hyperbolic of x by xi plus C2 sin hyperbolic of x by xi, where xi will be root over h square by 2m star v0 minus e0. Okay, okay. Now from this we can calculate current as uh, so the current density will be 2e star by m star real psi star uh, minus I h bar psi, sorry, grad psi. So this is nothing but it's just the current density expression uh, for quantum mechanical system written as a real part. Okay, usually we had psi star grad psi minus psi grad star psi grad psi star etc. This is just written in terms of real term, real part, but the basic equation is that only. Okay, now to use now before we use psi here in the current density equation, what we need to do is that we need to I mean evaluate the I mean the wave functions according to the boundary conditions. Okay, so we have psi at minus a, or rather, it should be a by 2 actually, because that's where the boundary is. So here we have a by 2 and plus a by 2. So the psi at a by 2 minus a by 2 is, assume that, yeah, let's say root over n, again this is n is the density, so n l e to the power I theta, so phi l, and then we'll have psi of a by 2 equal to root over of n r e to the power I phi r. Okay, so what we are assuming, so what this essentially means is that we have a uh, region something like this. So we have minus a by 2 plus a by 2, then we have a barrier. This is the insulating region, and this is superconducting on the left side, and then superconducting region on the right side, right? So wave function, we had deep inside the left region and right region, wave function is constant. So again it's constant, and then it decreases, and then the similar thing happens here as well. So on the right side also it is constant, and then it decreases, right? Should be symmetric, but yeah. Okay. Now, when we evaluate the wave function at plus a by 2 or minus a by 2, we can actually assume that it is almost the same as this, right? So at plus a by 2, whatever the value was deep within the superconducting region. So that's what we are doing in this boundary condition. Okay. And this wave functions, psi of minus a by 2 can be rewritten as, uh, 2e, 2 is the charge, and then m star h bar. So once you use these boundary conditions, then we can arrive at, these are the conditions, this will be the condition, c1 star c2. Yeah, so this will be the, so from this, using this wave function, we can arrive at this. Okay, okay, then we can write, yeah, so I should show the calculation actually, but the final result, I'll do the calculation and then upload. But so the current will be, again, so what we got, jc or j0 in our case, sine delta, and it will be proportional to, so basically j will be proportional to root over nl nr, as you have already seen, and then associated with some other terms. Okay, so I'll calculate, it's a big calculation, and then upload. Okay, so the next question is, but the idea was already, I mean, the established, in the generic case, what we have done here, this was the special case. So here, so when we did the Josephson junction, we have not assumed that, where the boundary lies, or what was the region of insulating region. But here in the question, it is precisely mentioned that I have a boundary potential for the insulating region from minus A by 2 to plus A by 2. So that's the extra thing that we need to do in this case. Okay. Earlier we solved for a generic case without any boundary condition, just the generic solutions, they looks like. But in this case, we have a particular setup in mind, and that we need to solve. Okay, the fourth question is draw the screening current and IS as a function of the applied magnetic field in a squid setup. Explain the variation and then present a schematic plot of the output voltage as a function of applied magnetic flux. Okay. Okay, and then the fifth question is also precisely the same actually. I mean, it's just the Josephson junction, what we have already done in question, what we need to do in question uh, 3 actually. It's just the same, they change the parameters, minus a by 2 to a by 2, but in the question 5c, it is minus a to a. It's just the change in parameter, nothing else. Okay. Okay, so the question 3 and 5 are actually same. Now the question is 4. The squid part is left. Okay. So let me go to the squid part. So I'll solve the generic squid problem, and then the solutions for the given expression, given questions are actually follow from there. Okay. Okay. So imagine we had this Josephson junction, but I'm writing, I mean drawing from a different angle. So, so earlier we had something like this, right? I'm showing the view from a different, so I'm showing the top view, let's say. So we have a superconducting region. So this is, let's say, superconducting region. Uh, so this part is superconducting region. And then we have insulating, right? On the normal region. So this is insulating region or normal region. Now we also have applied external magnetic field. So so let's say external magnetic field is applied along the I mean perpendicular to the plane of this paper, and they are going inward, let's say. Okay, so this is the direction of the magnetic field, inward B. Okay. Okay, now we consider a loop which is something like this. So these yellow regions are superconductor, SC region. Okay, and then this part is, let's say, lambda. So lambda is essentially the London penetration depth here. So so this part is, let's say, lambda. So what this lambda physically mean is that I have applied an external magnetic field. So the external magnetic field is definitely finite here, but then they can also penetrate up to this length. Okay, so up to this length. So that's the physical interpretation of lambda. And this thickness of this insulating or normal region, so this part is T, let's say. Okay. Now let's come to the second Ginsburg-Landau equation that we have discussed in the very first, in the beginning of this lecture tutorial is that we have m by 2e square closed loop, sorry, over C. So this is the loop C. So so loops. Oh, okay. I should use different because C point is already there. So maybe S is the loop. Okay, or S is even better. So some loop L. Okay, over a closed loop L. And we had equation like a0 is again associated with the London penetration depth and so on. J dot dl uh, mod psi square plus phi b flux through the loop, and then n phi 0, right? And n phi 0 was so h bar by 2e closed loop L gradient of phi dot dl. Okay, okay. Now if we have, let's say, because we have not applied any current, so J is 0 definitely. So the J is 0. So we have that uh, closed loop integral over grad phi dot dl is equal to, so so this part is 0. So we have phi b, so phi b. So this implies that phi b equal to h bar by 2e closed loop integral grad phi dot dl, right? So this we are rewriting as 2e by h bar surface integral over this closed loop. I mean the surface created by this. So this is the surface by this ABCD loop, and where we can write this as, so this loop integral we can I mean dissect as a to b grad phi dot dl. So this is the path a to b, okay, and then plus uh, b to c, this vertical path b to c grad phi dot dl plus then c to d grad phi dot dl plus uh, d to a equal to uh, 2e by h bar, let's say 5e. 5 is the flux, so this part. Now note that this the grad phi over a to b is 0. Okay, so this grad phi over this path is 0, and then from c to d is also 0. Why this is 0? Because we are still within the superconducting region 1, let's say. So let's say this is region 1 and this is region 2. Because superconductors, I mean superconducting electrons or Cooper pairs have a wave function with uniform phase deep within the superconducting region. So as long as we are in this in the same superconducting region, we are having the same phase of the wave function. So A to B grad phi is 0, and so does for C to D. So then it translates. So you can write this as a phi, and let's say this is superconducting 1. So we write as a phi 1 C minus phi 2b. I'll explain what do we mean by phi 1 C and phi 2b, and plus phi 2a minus phi 2 uh, sorry so phi 1 C minus 5, it should be actually 2. Yeah. Okay, so what do you mean by 5 or 2C is that C point is in the region 2, right? So this particular part, so this part we are writing as here, and this part we are writing as this. So phi, so grad phi means del phi del L essentially, and then dl, right? And as we take infinitesimal region, so this is enlarged. ABCD has been shown very, I mean, it's an enlarged view. So imagine we actually take very, I mean, small region within the superconducting, I mean, the Josephson junction. So this is A point is at x, let's say, and then B point is at x plus dx, where dx is much, much smaller than x. Okay. Okay, so then we can almost approximately write that that this particular part grad phi dl is essentially del phi dl, so it is equivalent to phi at that point. Okay, so phi to C denotes that the C point is in superconducting region 2, and then it is evaluated at C point. Okay, phi 1b again same, superconducting region 1 at B point. That's what the its meaning, and then we want to reshuffle it. So, so what we do is that phi to C minus phi to D. Okay. Right. So what I need to do is that so I need to evaluate phase at x plus delta x. So this is fine actually. Yeah, fine. So I just will have this only. So phi 1b, and then I want to do phi 2d minus phi 1a. Okay. So just nothing but reorientation. So here it was plus, we have taken extra minus, so we reshuffle this and this. Okay. Okay. So now see this, that what is phi 2c minus phi 1b? Okay, from here. So phi 2c and phi 1b. So this is the difference in phase at the same point x plus dx between these two regions, right? Right. So this we can write as delta of x plus dx. So delta is the phase difference between these two superconducting region. Okay, so this we can write as this, and minus delta of x. And what is delta of x? Again, so this phi at 2d, so phi 2d this was here, and minus phi of 1a, right? So again the same thing, the phase difference at x between these two region d and a. Okay, so this will write as 2e by h bar phi of b, and this is essentially for small region we can write as d of delta of x. D is the derivative. Okay, and it will be uh, 2e h bar. Now phi b is the flux. Flux means b into the area, right? And the what will be the area? 2e h bar B is the applied magnetic field, and the area will be T plus 2 lambda, right? And times the dx. So why this will be the area? Because uh, so we had the T effective. So T effective is T plus 2 lambda, because T is the thickness of this region. And then in both the sides of the superconductor, the magnetic field can penetrate up to the lambda London, according to London equation, penetration depth is lambda. So this is lambda, and then in this region also we have lambda. So T plus 2 lambda is the thickness, effective thickness for the magnetic field, and then dx is the length, right? So the area will be, this is the area, dx times the T plus 2 lambda. So this means that uh, we have d of delta of x by dx equal to 2e by uh, so 2e by h bar b T effective. So T effective is again equal to T plus 2 lambda, and then yeah, so that's it. Then if we integrate this, 2e by h bar b T effective times x plus delta 0, some constant delta 0. Okay, so this is the phase difference at x point between two superconductor, I mean two superconductors actually, yeah, in the Josephson junction. Now plug this into the current equation we had. So the current density was J equal to Jc or J0 sine delta. So this will be equal to sorry, Jc sine of 2 pi b T effective into x by phi 0 plus delta 0. So phi 0 we have written because uh, h by 2 pi, 2 is phi 0. Okay. So from this, so this is to the, from this to this we have used this equation. Okay. Okay. So this can be rewritten as just the reorientation sine of 2 pi x by lambda j plus delta 0. Okay. Where lambda j is defined as phi 0 by b into T effective. Okay, and this is the characteristics length scale along the junction actually. Okay, so this is the, I mean, explicit expression of current through a Josephson junction, and it shows that it depends on the I mean the position you are at the Josephson junction and so on. Okay. Okay, now comes the squid part, let's say. So we have current density. So the current, so if we calculate the current, sorry, okay, just a second. Okay, so we have the current density, so we can calculate current as just the integration of it. So Jc and then sine of 2 pi x by lambda j plus delta 0 dx or ds, right? ds is the surface area, elemental surface area. Uh, we assume that the ds is, so ds is w into dx, right? So the current is going from, so we had this simple picture. We had region 1, region 2, and this was, let's say, along this it was x, right? And then current was flowing from here to here, one junction, I mean, one region to another region. Now that this was the thickness, and we assume that the width is in plane direction, inward direction. This is the width. Okay. Okay. So assuming this, we have Jc is constant, so it is out of integration, and then W integration over sine 2 pi x by lambda j plus delta 0 dx. Okay, and the limit for the x will be, let's say, minus L by 2 to L by 2. So we assume that so let's say we have junction like this, and then somewhere here the origin, so this is sitting at minus L by 2 and then plus L by 2 x. So minus L by 2 to L by 2. And how do I integrate this? This is just the real part of, so we can integrate this by L by 2 to L by 2. Real part of minus iota, sorry, plus I, e to the power I, or rather minus I, so that plus I times minus I is plus 1. This will be 2 pi by lambda j x plus delta 0, right? And then dx. So this is nothing but the reorientation. So this sine function we can write like this. Now it is easier to do for the I mean exponential, integration of exponential. We could have directly done the sine, I mean the integration of sine as well. It's not a problem. So we have jc w real of I e to the power I 2 pi x by lambda j plus delta 0 by this will be minus I by 2, and then jcw. Okay, so so this I cancels out, and then it is just the negative, and then uh, so lambda j by 2 pi, uh, so real part of e to the power minus I 2 pi uh, L by 2 lambda L plus delta 0 minus e to the power minus I 2 pi L by 2 lambda L. So here this will be minus L plus delta 0, right? So this is the so we are doing calculation of current. Yeah, so this will be current actually. Okay, Okay, now if we reorganize this, we can finally write as IC0, where so let me write and then explain. Sine of phi b by phi 0, and then sine of delta 0. Okay, so where we have used this uh, transformation. 2 pi by 2 lambda j is nothing but 2 pi by 2 phi 0 times the b times it was the area, right? So T effective, and then we assume the length is L. Okay, so this is the area, and then we can write it as a pi phi b. This part is phi b by phi 0. Okay, and we also wrote IC of 0 is JC times W width and times the length. Okay, okay, so this is final expression IC of B. So this part depends on the magnetic field just because phi B is magnetic flux, right? Which depends on magnetic field times the sine delta 0. Okay. Now this ICB is IC of 0 mod sine phi B by phi 0 by phi B by phi 0. Okay. And this almost looks like so this similar kind of equation actually appears in Fraunhofer diffraction. So if we plot this with respect to phi b, let's say, so suppose we are varying phi b or equivalently the magnetic field, we have something like this. So these things should be symmetric, but yeah, something like this. Okay, so this is IC of b, and it will be finite, I mean 0 at phi 0, and then again 0 at 2 phi 0, and then amplitude will also decrease with phi b. Okay, so at phi b, so whenever phi b, the magnetic flux become exactly equal to the flux quantized, I mean the fundamental flux phi 0 or its integer multiple 2 3 and so on. The current density actually, or the current actually goes to 0. Okay, so this is one of the key principle by which you can determine the current. So you can vary the I mean you can see the you can uh, you can actually detect where the minima comes. Okay, meaning so suppose you have a Josephson, I mean in some region we have some magnetic field applied. Okay, and you take the Josephson junction there. So these are, let's say, magnetic field, and you take the Josephson junction there. So some device Josephson junction, and you I mean see the variation of let's say current in the Josephson junction versus the magnetic flux. Okay, so so let's say you get the first minima of the current at some point, right, at some flux. So you know that the minima occurs at precisely at phi 0. Phi 0 value you already know. This is nothing but h by 2e, right? So this has a constant value. Now phi b you need to determine. So we have phi b equal to b into the length of the Josephson junction and times the effective T effective, right? Effective thickness. Now T effective also you know, because how much thickness of the insulating region we already know. That's how you make it. And given a material, what is the penetration depth? You also, I mean, sort of you have an estimate of that. So from this equation, the only thing unknown is the magnetic field. L we know, and then T effective we also know. Phi 0 is anyway a constant. So that's how you can calculate what will be the B in that region. Okay. Uh, so just for a typical estimate, so if you take, let's say, uh, length to be 1 millimeter, let's say. These are anyway very small devices, right? So we are in the quantum mechanics, so small scales, length scales. And let's say I mean, the thickness is 1 millimeter, and then not thickness actually. Thickness 1 millimeter is too much. So length is 1 millimeter, and then the thickness of the insulating region, let's say few hundred nanometer. Okay, so maybe 10 to the power 2 nanometer. Okay, okay. So if you estimate this using phi 0, then you will see that B is of the order of maybe zero point 0.1 Gauss. Okay, so basically 10 to the power minus 1. So this is the, I mean, from this equation, you can actually determine that B is of the order of zero point 0.1 Gauss. You can measure using uh, Josephson junction. We are still not in the squid. Okay, so that is one drawback, let's say, or not even the drawback, but that builds on the squid basically builds on this principle of Josephson junction. Now, in Josephson junction, what we had is simply uh, I mean, two superconducting region and one insulating region clubbed together. Now in the squid, we do something more with the Josephson junction. So what we do, in general, there can be many different types of squid, I mean different shapes of squid, but one of the, I mean, sort of very well studied is that we have a circular loop, something like this. Okay. So here we have, so we made Josephson junction something like this. Okay. So this is the insulating region. This is again the insulating region, right? And then, so if we cut here, so this part, then we have only single Josephson junction, right? Because you had a, I mean, so this is one Josephson junction, superconducting region, let's say 1 and 2, and then they are separated by this insulating region. Again, here also the same, 1 and 2 separated by insulating region. But what to do is that we create two Josephson junction, and then I mean, we make a single device. Okay, and this is something. So then if we have something like this, and then uh, applied, we have applied magnetic field here also, right? And we are sending current as usual. So then current in the sample will be IC equal to, let's say, total. So IC, and again this will be dependent on the magnetic field we have just seen, sine delta 1 plus IC of B sine delta 2. Okay, so this is, let's say, delta 1. So so there are two Josephson junctions, so the total current via this will be I, and this will be given by this. Okay, okay. Now this phase difference of delta 1 and delta 2 again we will determine from the uh, I mean, from the equation we had. So this will be a closed loop, let's say somewhere we have a closed loop. uh, so this is, let's say this is closed loop C. Then we have gradient of phi dot dl equal to 2 pi of phi 0 flux, right? And this will give us, again similar to the case we just derived, delta 1 minus delta 2 will be 2 pi phi of B by phi of 0. Okay, okay. So now use this equation in this equation. So current will be now 2 IC of B So sine delta 1 plus sine delta 2, we can write as delta 1 plus delta 2 by 2, and then cos delta 1 minus delta 2 by 2, right? So that means we'll have 2IC of B, or rather now 0, and we're writing so we're writing the value of ICB. So we have sine phi prime by phi 0, uh, pi of phi prime by phi 0, and then cos of phi by phi 0. I'll explain what are these terms, and then sine of delta bar. Okay, so sine of delta bar is nothing but this part. Okay, delta 1, so delta bar is delta 1 plus delta 2 by 2. So the average phase. Now cos, in case of cos delta 1 minus delta 2, which is the phase difference, we have written this. Okay, okay. And then ICB was the magnetic field dependent current written here. So this part we have written here, and we have changed the notation here. Here it was phi, right? Phi B to be phi prime. So now there are two flux associated with. So this is really important. So we have phi prime is different color. So phi prime is magnetic flux enclosed in each Josephson junction. Okay, and then we have phi B within the squid loop. So let me redraw the figure, then it will be clear. Okay. Uh, so suppose I have, okay, so let's say this is my insulating region. So this is my insulating region, and again we have insulating region. Okay, and so there is some magnetic field applied all over the space, and again we are also applying current. Now here the phase is, let's say in this region the phase is delta 1, this region phase is delta 2, and in between we have a small, let's say, closed loop. Okay, so this is, so the flux associated with this region is phi prime. This is also phi prime. We imagine that the Josephson junction, both of the junctions are identical, so both are phi prime, and this is the phi b, okay, of a loop. So these are the two fluxes. Now the interesting part is, in contrast to the single Josephson junction, here we have two Josephson junction. Now the current In the single Josephson junction, we have current variation with the flux because of this term, right? We have additionally this term as well because of two Josephson junction. Okay. Now, if we I mean draw the current versus flux now the current as a function of magnetic field will have these two terms, right? So this we now as re- write as ICB, okay, including IC0, let's say. Now, if we plot this, then what you will see is that this is, let's say, IC of B, and again this is phi B. So as usual, we'll have big envelopes somewhere here and so on. And what we'll see additionally is that it's there will be some small oscillations, rapid oscillations. Okay. So the nodal point corresponding to this part, we already know from the Josephson junction that it can detect magnetic field up to, let's say, zero point 0.1 Gauss, right? And this nodal point, you can do the analysis here as well, and it turns out that these minimas, these minimas at the so this minima is due to the this part. So how should I show it? So this minima is due to the sine phi. Rather, we had pi phi prime by phi 0 by pi phi prime by phi 0, right? So these big minima are because of this, and this small minima are due to the cosine of this term, this new term. Okay, pi phi b by phi 0, phi 0. Okay. Okay. Uh, yeah. And if you just roughly do the calculation, so this phi, this nodal points actually corresponds to the magnetic field of 10 to the power minus 8 Gauss. Okay. So you can already sense that the phi b, the at a very small magnetic flux, this is we are getting nodal point, right? So that means the magnetic field it can measure, it will also be very small, and you can go literally up to minus 10 to the power 8 Gauss. So that's the advantage of SQUID actually. So you can measure absolutely very small magnetic field which we are not able to measure, or we can only go up to 10 to the power minus 1 Gauss using a single Josephson junction. But when you create or merge two Josephson junction and create a SQUID like device, then the magnetic field detection limit goes far below. Okay, so that's the point of using SQUID actually. Okay, so that's the SQUID part, I mean current derivation. And current versus voltage for SQUID will be something like this. So, so you have voltage, that's an independent function. So IC of V, let's say. So we have for a substantial amount of voltage, the current is there is no voltage in the system, so that it's essentially superconducting, and then after certain time there is a voltage developed. Okay, so that is, let's, yeah. Now if we apply magnetic field, then of course the voltage, I mean the superconductivity will destroy at a less critical current density. So somewhere here, So this is, let's say, IC of B, and this is IC of without any magnetic field, let's say. Okay, and this is IC 0. So this part is IC 0. Okay, so the critical current density, actually it should be more clearly drawn. Critical current density should appear at less current actually when you apply magnetic field, something like this. So here earlier we had here, but then once you apply magnetic field, it gets lowered. Okay. Okay, so that's the squid part, and yeah, the assignments is roughly done. Actually, actually all the questions are from the lectures itself. So any questions?
No.
Okay, if not, then maybe we can stop here. Okay, bye.
Okay, thank you.
Yeah.